So in the previous video, we were doing some examples, solving differential equations. But if you see in every single problem, we had this constant of integration, which was c, okay? So we wanted to figure out what that constant was. So how do we figure that out? So these are what we call initial value problems. So we call them IVPs for short, initial value problems. So usually what you want to be able to do is, well, what are we going to solve for? How do we solve for C? So basically what we do is we need additional information. So we need some additional info to find out what is this differential equation really modeling. And usually what we have is something called an initial condition. So what it might look like would be something like this. So you might have y prime is equal to 6x over y squared with initial condition y1 equals 2. Okay, so this guy right here, this guy is what we call an initial condition. Now you might be wondering, what exactly is this? Well, imagine that we have like y of x equals, I don't know, a. Okay, so basically we're saying that at x equals 1, my y value is 2. Okay, so this is going to be basically your x value, the thing that's in the inside, and this is going to be your y value, kind of how you had f of x. Okay, so we have some additional information. So maybe if this was modeling time, at time equals 1, maybe the temperature was 2, I don't know, something like that. So, so why don't we go ahead and try to solve for this differential equation? Okay, so let's just say solve the differential equation. Okay, and we're gonna start off with that one that we just had. Y prime is equal to 6x over y squared with initial condition. I'm gonna write just IC for initial condition. Y of 1 equals 2. Okay, so the way that we're gonna do this is that we're gonna be dealing with this later. So we're gonna do this the same way that we were doing the other problems. We're just gonna go ahead and just write y prime is just gonna be, so y prime here is gonna be changed to dy over dx. Is gonna be equal to 6x over y squared. Okay, so now something that we can do is that we can just kind of cross multiply. Okay, so this is just going to give me y squared dy is equal to 6x dx. Okay, so now the next thing that we want to be able to do is now we want to go ahead and take the integral because we've already separated this. So take the integral, take the integral. So this is going to give me y cubed over 3 is equal to 6x squared over 2 plus c. Okay, so let me clean this up a little bit. So y cubed over 3 is equal to 3x squared plus c. Okay, and now what I'm going to do is I'm going to apply multiply it by 3 first. So I'm going to multiply this whole thing by 3. So y cubed is equal to 9x squared plus c. And then we're going to apply a cubed root to both sides. So we're going to have y is equal to the cubed root of 9x squared plus c. Okay, so if we didn't have an initial condition, this would be the answer. But now because we know initially what this was, I can actually figure out what this particular solution will be by plugging in this initial condition. So all this means is that I'm going to now do y of 1 equals 2. So right now we have y is equal to the cubed root of 9x squared plus c. So one thing that we can do is that you can kind of think about this like this. So y of x is equal to the cubed root of 9x squared plus c. So changing the y to y of x, because you know how y is the same thing as f of x, you can kind of change it like this. So now what we're going to do is we're going to go ahead and plug in this 1. So y of 1 is going to be equal to the cubed root. So wherever I see an x, I'm going to plug in a 1. 9 times 1 squared plus c. And now we're going to solve for c. Now y of 1 was just equal to 2. So 2 is equal to the cubed root of 9 plus c. We're going to get rid of that cubed root by applying a cube to both sides. So I'm going to be left with 8 is equal to 9 plus c. Then we just solve for c. So c is equal to -1. So now that I know what c is, I can figure out what my differential equation is. So this particular solution, y is going to be equal to the cubed root of 9x squared, and c was -1, so I'm going to plug -1. So this is the true solution. So what this means is that if I were to take the derivative of this and plug it into the original differential equation, it's going to give me this thing. Okay, that's basically what that means. Okay, so let's do another problem. So let's say, for example, we have dy over dx is equal to x to the 4th times y. Okay, all right, so now what we want to be able to do with these problems, let's first start off with separation of variables. Oh, I forgot to give you the initial condition. With initial condition, y of 0 equals 2. Forgot to give you that. Okay, so now let's apply separation of variables. Okay, let me multiply by dx to the other side. So I have dy is equal to x to the 4th y dx. Okay, I haven't separated everything yet because you notice that I have a y still on this side, so I'm going to move the y over by dividing it. So now I'm left with 1 over y dy is equal to x to the 4th dx. Now I'm going to apply an integral to both sides. So the integral of 1 over y is just going to be ln of absolute value of y. The integral of x to the 4th is just going to be x to the 5 over 5 plus c. And now how do we get rid of a natural log? Well, the opposite of taking a natural log will be to exponentiate both sides. So take an e. So that's going to go ahead and get rid of it, and I'm going to be left with an absolute value of y is equal to e to the power of x to the 5 over 5 plus c. So the plus c is also still on the top. Okay, notice that it's e to the whole thing. So this whole thing is on the top, on the exponent on the e. Okay, now usually this absolute value means that there's going to be a positive and a negative value. So we'll deal with the absolute value in a little bit. But what I'm going to do is I'm going to do a little trick here. Okay, so to make it a little easy, so I'm going to have absolute value of y is going to be equal to e to the x to the 5 over 5 times e to the power of c. So this is just properties of exponents, what I'm doing here. This e to the c is just a constant. If I take e to the power of something, that's just going to give me a constant. So you have absolute value of y is equal to, let's just say this constant is going to be another c. c e to the x to the 5 over 5. Okay, now this absolute value just means that the y value can be positive or negative. So y can either be positive or negative, c e to the x to the 5 over 5. Now, lucky for us, this positive or negative is just basically, with the c, is just another c. So y is equal to another c e to the x to the 5 over 5. Okay, so that's what this guy is going to be. Okay, so a lot of algebra. Notice that all of this was just algebra. It wasn't even any calculus. The calculus was easy. It was just the algebra part. Okay, now what we got to figure out is figure out what the c is. So we're going to use that initial condition. So y of 0 equals 2. So this guy is going to be y of x is equal to c e to the x to the 5 over 5. Now we're going to go ahead and plug in the 0. So y of 0 is equal to c e to the 0 to the 5th power over 5. We know that y of 0 is equal to 2 c e to the 0 power. E to the 0 power is just 1. So that means c is equal to 2. So if I want to find my particular solution is going to be y is equal to c, which is equal to 2 e to the power of x to the 5 over 5. Okay, and that's going to be my solution. Okay, so these problems can be really difficult, especially when it comes to the algebra part, because the algebra part is the thing that's making it a lot more algebraic. So you want to be able to be careful with that. Also, some things to consider is be able to do a couple tricks. So sometimes problems may not seem separable, but they might be. So for example, y prime is equal to xy minus x. This kind of looks, well, I don't think this is separable. Well, you can kind of change this to dy over dx. And then what you might want to do is you want to factor this. So I can factor out a value of x, and I'm left with y minus 1. So see that now I have a function of x and a function of y, which I can easily do. I can move the dx over, so I have dy equals x, y minus 1 dx. And then notice that I can divide by this y minus 1. So this goes away, and I'm left with 1 over y minus 1 dy equals x dx. And then after that, I can now apply an integral to both sides. So sometimes you might want to be able to do these little tricks. Also, be aware that when you do an integral, sometimes you might have to use integration by parts. So sometimes it might not just be an easy integration where you might have to just do just the integral. Sometimes you might have to do u substitution, or sometimes you might have to do partial fraction decomposition. So hopefully it doesn't get to that. But these, remember now, you want to apply any integration method that you have learned in this class. Okay, even if you've forgotten it, go ahead and freshen up on those skills. So just don't forget these. Make sure that you are ready to do problems like these, so they can get really complicated. But you already know how to use these integration techniques.